Chapter 2. What are or is data? Section 2.1. Is data singular or plural? Please forgive my rant about grammar usage. I'll keep it short. Grammatically, data is a plural noun. Data means multiple data points, i.e., more than one piece of data, a countable collection of data values. One piece of data, that is one data point, is a datum. Datum is the singular of data. One number is a datum, two numbers are data. Therefore, writing or saying, this data shows, or the data was uploaded, should be a forgivable grammatical mistake that a non-native English speaker would make. Proper grammar dictates these data show and the data were uploaded. Or this datum shows and the datum was uploaded. But instead, somehow, and much to the chagrin of statistical grammarians, data became singular yet plural. This data shows became acceptable in media and communications. There's even a Reddit subpage called Data is Beautiful. Oh, it grates on my ears. It's cacophonous. It's like a centenarian witch scratching her overgrown fingernails down a chalkboard while singing that terrifying jingle from Dario Argento's Suspiria. Granted, I do not have perfect grammar, and I'm sure that a fine-tooth linguistic comb will discover a smattering of grammatical mishaps in this book. But I will unerringly use data as a plural noun and datum as a singular noun. All right. Thank you, dear listener, for tolerating my rant. Let us now turn to a more meaningful discussion about data. Section 2.2. Where do data come from and what do they mean? The universe is a really, really, really unfathomably complex place. We don't even understand how complex it is. Indeed, around 95% of the universe is elusive matter and energy of the dark variety. And yet, we are curious creatures. Humans have long tried to understand and control their environment through stories, fables, religions, philosophies, observations, and science. The scientific approach to understanding the universe is to build measurement devices that convert some physical observable into a number or a set of numbers. And those numbers are called data. Here's an example. Imagine that you work for a company that wants to understand its customers better. Of course, people are really complicated and diverse. So to help you understand the customers, you devise a measurement device, a questionnaire, in which customers give numbers in response to questions about their preferences for different products or designs, or perhaps how much money they would pay for some products or services. Those numbers are data. But here is the important thing. Those numbers are not reality. Reality is much more complicated and nuanced. A customer's satisfaction with a product is not literally 9 out of 10. It is a subjective experience that involves a confluence of emotions and memories and expectations, genetics, and myriad other factors that might include what they had for breakfast that day and their spouse's stress levels. But that totality of biopsychosocial emotional dynamics that produces their satisfaction is just unfathomably complex. It would take a lifetime of scientific work to even begin to understand, let alone accurately measure. So instead, we try to capture some essence of that reality in a number that we can store in a spreadsheet. And those numbers, the data, they are not reality, but they do reflect measurements of reality. So this is where data come from. We develop measurement techniques to translate physical and biological phenomena into numbers that can be stored on a computer. Those measurement techniques might be technologically sophisticated, like a super collider, an MRI machine, or an electron scanning microscope. Or the measurement techniques might be simple, like a questionnaire, a weight scale, or a medical expert's rating of disease severity in a patient. The quality of the measurement device is important because it is related to the accuracy and the precision of the data. I'll discuss these terms in more detail in section 2.5. But conceptually, all data are the same. You measure something in the universe, that measurement produces a number or a series of numbers, or maybe it's text that get converted into numbers, and we call those numbers data. You apply statistical analyses on those data in hopes of better understanding the system under investigation. Section 2.3, what do data look like? For processing and analyses, data are digitized and stored on a computer. Therefore, data are fundamentally coded as binary states of a series of memory cells in your hard drive. But we represent and we visualize them as numbers and letters that are familiar to us. Most datasets are represented as numbers in a table, with rows corresponding to data samples and columns corresponding to measured characteristics. In other words, the rows correspond to observations, and the columns correspond to features. Figure 2.2 shows an example dataset. I rated my early afternoon coffees at the co-working space where I was writing this chapter. Each row is an observation, and each column is a feature. This table shows that data features can be categorical and encoded using text, or they can be numerical. There's also a missing datum because I was slightly hungover on Saturday and didn't go to the co-working space. So figure 2.2 shows a table. The table contains 3 columns. Column 1 is titled Day of the Week. Column 2 is titled Coffee. Column 3 is titled Enjoyment. Below the feature labels or headers or variable names are 7 rows corresponding to each day of the week. So the first column goes from Monday, Tuesday, Wednesday down to Sunday. The second column is the category of coffee, the type of coffee that I drank on that afternoon: iced cappuccino, espresso, iced mocha latte, etc. And the third column, labeled enjoyment, is numbers out of 10. So 10 out of 10, 8 out of 10, 6 out of 10, and so on. Figure caption reads, a small data set I collected. Enjoyment numbers are my subjective experience of the coffees out of a maximum of 10. N/A, which is the value listed instead of a number for Saturday, stands for not applicable. This is a missing data point. Back to the text. Data can also be in the form of images, which are represented as numbers that are mapped onto pixel color intensity. Some datasets may be stored as multidimensional arrays, like a 3D cube instead of a 2D sheet of numbers. Color images, for example, are often stored as a cube, with width, height, and RGB colors being the 3 dimensions. That paragraph refers to figure 2.3, which shows on the left an image of the number 6, and on the right, a 2D spreadsheet of numbers corresponding to pixel intensity. So there's a lot of zeros, which correspond to the black background, and then higher numbers getting closer to 250 for lighter pixels. Back to the text. But the data sets that are most relevant for statistical analyses discussed in this book are represented as spreadsheets with observations or samples in the rows and features or measurement variables in the columns. Data can be numeric or text, which I explained in figure 2.2. That was the figure about the coffee and enjoyment of the different coffee types. However, non-numeric data are usually converted into numbers for analyses. For example, the data in column coffee can be converted to 0 for cappuccino, 1 for espresso, and so on. Notice that this mapping of data category to number is arbitrary. Why not 1 for cappuccino and, 2.3 for espresso? In some cases, this numerical mapping has implications for interpreting the results. For example, in a regression analysis, you will learn about why that is later in the book. For now, suffice it to say that text data are often converted into numbers. Now, for data sets that are relatively small, you can literally just look at the entire data set. You can see the entire spreadsheet of the data set. Having a bird's eye view of the entire data set is great, but it does not scale to data sets that are large or multidimensional. Furthermore, just looking at a spreadsheet of numbers does not necessarily lead to insights, nor is it reasonable to think that you can see meaningful patterns in the data simply by looking at the raw data. So data visualization is necessary, and you will learn many data visualization methods in the next chapter and throughout the rest of the book. Section 2.4, Limitations of Data. If data come from measurements of the universe, why do we need data processing and statistics? Can't we simply trust the raw data? Unfortunately, there are several reasons why not all data are immediately trustworthy and therefore require cleaning, preparation, normalization or transformation, and statistical analysis. Below, I will list some of the problems that plague the quote-unquote raw or unprocessed data, and that motivate application of algorithms or analyses to the data before they can be interpreted. Concerning data that come from imperfect measurements. The quality of the data is limited by the quality of the measurements. So here's a few examples to highlight this limitation. Example 1. You ask people to report their purchasing preferences from 10 years ago. So you put this survey online, you get tens of thousands of people to provide data, but what do those data actually mean? Do they really reflect people's past economic decision-making? Or are you actually measuring their memory or maybe their idealized images of their past selves? Example 2. It is important to measure the temperature inside of an engine, but a thermometer placed inside the engine will melt. So you might think of placing a thermometer just outside the engine, but then that temperature measurement reflects a combination of the engine temperature, the outside temperature, and the heat transmission through the engine casing. Footnote. In fact, engine temperature is best measured through electrical resistance. This example is more for your conceptual understanding than explaining automotive engineering. End footnote. Example 3. In early 2020, the novel coronavirus spread across the world, and countries tried to count the number of infected people. But although the virus causes death or severe health consequences for some people, many other people have no or mild symptoms. So, in fact, the data showed the number of reported cases, which is not the same thing as the number of infected people. The number of infected people is a much more important number than the number of reported cases, and yet was extremely difficult to measure, certainly before self-tests were widely available and when testing only people who experienced moderate to severe symptoms. The point is that you always need to think carefully about the data, where they come from, what they actually measure, and how closely they match the phenomenon of interest. The larger the gap between how the data were measured and the system you're interested in, the more difficult it is to interpret the data in context of the research goal. For example, a thermometer outside the engine is not the best way to measure internal temperature, but it certainly is better than a thermometer on the hood, so outside the car. Concerning data may contain noise. Another limitation is that data often contain noise. Noise is a surprisingly difficult concept to define, but can generally be thought of as unwanted variation in the data. Now, some noise has known sources, for example, the 50 hertz or 60 hertz electrical line noise in unshielded wiring. Some noise is due to faults in the measurement device, like a grease smudge on your phone camera will decrease the quality of the image. And some noise is due to unknown or unquantified sources. For example, people's weight is determined by a complex mixture of genetics, age, lifestyle, and other factors. Noise can be non-systematic, meaning it affects all measurements equally, or it can be systematic, meaning it affects only certain measurements, or it affects measurements in a way that can introduce a specific bias or misrepresentation. Some types of noise are easy to minimize or ignore in statistical analysis, whereas other types of noise are more deleterious. You will learn about identifying and dealing with noise in Chapter 7 and quite a few other chapters. For now, I would like you to appreciate that noise introduces unwanted variation into data and can make the data more difficult to interpret. See Figure 2.5. Figure 2.5 highlights the fact that noise in the data can negatively impact statistical analysis and interpretations. There are two panels in Figure 2.5. The panel on top shows a scatter plot of x and y, two variables on the x-axis and the y-axis. The variables are very tightly related to each other. You can draw a line that fits the linear relationship, and most of the data points are tightly clustered around that line. The lower panel is titled More Noise and shows a similar linear relationship between variable x and variable y, but the data are much further distributed. They are much further away from the best fit line, meaning that the data are so noisy that it is more difficult to quantify and interpret the linear relationship between the two variables. Concerning outliers that may skew statistics. Datasets sometimes contain a small number of data points that are unusual relative to the rest of the data. These data points are called outliers or non-representative samples. Outliers can arise for a variety of reasons, such as measurement errors or unusual data values. Outliers can have an outsized impact on the results or no impact at all, depending on the nature and the size of the outlier and on the statistical analysis being performed. It is often necessary to examine the data for outliers and possibly remove them from the data prior to analysis. More on this in Chapter 7. This paragraph refers to Figure 2.6, which highlights that outliers or unusual data values can cause problems in statistics, and you will learn strategies for how to deal with outliers. The figure itself shows a scatter plot of data where most of the data values are clustered relatively close to the x-axis, and there's one data point in the middle which is much, much higher than all the other data points. It's highlighted in light gray, whereas all the other data points are black, and that light gray point is an outlier. It is unusually large. Concerning what is a measurement unit. Most of the measurement units we use, like seconds, kilograms, miles, subjective reports, etc., are arbitrary and human invented. For example, a second is based on the state transition frequency of the cesium-133 atom. But why this particular isotope and not any other? A kilogram is 1,000 grams, which was originally defined as the weight of a cubic centimeter of water. But why a cubic centimeter, and why at a particular temperature, and why use base 10? A mile is 5,280 feet, which is, I don't know what it is, but I think you're getting the idea. To be sure, there are some measurement units that appear to be universal, meaning that they are the same everywhere in the universe. One example is the speed of light, which physicists believe is a constant everywhere in the universe. If you had to explain Earth transportation to a space alien, it would be better to say that we drive cars at 8.946989587 times 10 to the minus 8 C instead of 60 miles per hour. considering that both mile and hour are non-universal arbitrary units. Of course, there is nothing wrong with our human imagined units. They're convenient and they allow for effective communication. My point is that non-universal cultural measurement units are just one more step between the actual universe and the numerical values in our datasets. The conclusion from this section is the following. Although we like to think that data come from things in the universe that we want to understand, that is not the case. Instead, data come from measurement devices. If the measurement devices are inaccurate, noisy, or flawed, then the data may be difficult or impossible to interpret. And failing to understand the distinction between the universe and data may lead to misleading or incorrect conclusions. Section 2.5, Accuracy, Precision, Resolution, Range. The quality of measurement devices can be quantified in multiple ways. In this section, you will learn the definitions of and distinctions among the 4 terms listed in the section title. First is accuracy. Accuracy refers to the correctness of the data in relation to the feature it is measuring. For example, a cheaply made heart rate monitor reports that your heart beats 80 times per minute, when in fact your true heart rate is 50 beats per minute. So this is an example of low accuracy. In contrast, a higher quality heart rate monitor reports that your heart rate is 52 beats per minute, so that's higher accuracy, though still imperfect. Next up is precision. Precision is the device's ability to provide the same data value with repeated measurements. For example, imagine stepping on and off a digital weight scale 5 times. Now, your weight does not fluctuate over such a short period of time, and yet the measurements are 72.4, 73.1, 70.4, 73.2, and 72.1 kilograms. So this scale has low precision. In contrast, a higher precision scale might return 72.4, 72.5, 72.4, 72.2, and 72.3 kilograms. Minor fluctuations might come from variation in posture and weight distribution on the scale. The next term is resolution. Resolution refers to the numerical distance between successive measurements. For example, a low-resolution temperature sensor in a kitchen oven reports temperature to the nearest 25 degrees C. For example, 200 degrees, 225 degrees, 250 degrees. Whereas a higher resolution oven reports temperature to the nearest 1 degree centigrade. In signal processing and time series analysis, resolution is called the sampling rate or the discretization rate. And in digital image processing, the resolution is determined by the number of pixels. Next up is range. The term range refers to the smallest and largest values that the sensor is capable of measuring. For example, a thermometer that you put in your mouth to check whether you can convince your parents to let you stay home from school to play video games, to lay in bed all day, might have a range of 35 degrees to 42 degrees Celsius. It doesn't make sense to have such a measurement device report temperatures down to minus 100 or up to 300 degrees. Now, accuracy and range are rarely confused because these are concepts that we use in day-to-day life. Precision and resolution, however, are more often confused. Make sure you understand the difference between precision and resolution because you want to be that annoying person correcting someone else's mistake and not that embarrassed person who gets corrected. Figure 2.7 shows a series of bullseyes that are often used to illustrate these concepts. An ideal measurement device would produce dots only in the center of each bullseye I will now explain Figure 2.7. So Figure 2.7 illustrates 3 bullseye diagrams that illustrate accuracy, precision, and resolution. There are 6 dots on each of the 3 bullseyes, and of course the goal is to hit the center of the bullseye. So we have the leftmost bullseye shows all of the dots clustered tightly in the center right on top of the bullseye. This is depicting high accuracy, high resolution, and high precision. The center bullseye contains 6 dots that are arranged in a grid slightly spaced out, and they are up and to the right of the center of the bullseye. This depicts low accuracy because the dots are far away from the center, low resolution because the dots are arranged in a grid. They're restricted to a series of grid locations, and yet high precision because all the dots are relatively close to each other, indicating repeated measurements giving the same numerical value. And then on the right, we have a third bullseye with the 6 dots that are kind of clustered or distributed around the bullseye, but the average would be in the center. So this is depicting high accuracy, high resolution, but low precision because each successive dot or arrow is going into a different location, but they're all averaging around the center of the bullseye. If you have the print version, there's another 3 bullseyes underneath those 3 that I just described without any labels, and you can describe those bullseye patterns in terms of accuracy, resolution, and precision. Back to the text. Needless to say, accuracy, resolution, and precision should be maximized, but that is not always possible, partly because of technological limitations and partly because of the data you are trying to measure. For example, psychologists use self-report questionnaires to assess personality styles, but people might lack a highly accurate purview of their own capabilities. For example, 65% of Americans think they are smarter than 50% of the population. That is according to a research study. Low precision and low resolution can be overcome with repeated measurements and averaging. For example, imagine weighing yourself 5 times and taking the average as your quote-unquote true weight. Low accuracy is problematic because it can introduce systematic biases that lead to misinterpretations. Section 2.6, Data Types. Because I incorporate coding into this book, let me start this section by disambiguating data type in computer science from data type in statistics. In computer science, data type refers to the format of data storage. For example, int for integer, string, float, or bool for boolean. This has implications for the kinds of operations that can be done on variables and how much storage those variables take up in the computer's memory. In statistics, data type refers to the category to which data can be assigned depending on the nature of the data. The data type category has implications for the kinds of visualizations and statistical analyses that can be applied to those data. There are many different types that people have distinguished. Very broadly speaking, data can be numerical or categorical. Categorical is sometimes also called labeled. Now, there are finer distinctions within each of those broad categories. I depict this in figure 2.8, but the figure is actually just showing a table and the text describes all of the elements in the table. So I will now go through all of the rows for deeper explanations. First up is numerical data. So numerical data comprise numbers, but it's not just about being numeric because categorical data can also be represented as numbers. The defining feature of numerical data is that the data values have some meaningful connection to the quantity in the universe that those data reflect. For example, if you have 47 apples, then the number 47 meaningfully relates to a physical quantity in the universe. In contrast, if we have categorical data, we assign BMW equals 1, Mercedes equals 2, Honda equals 3. then there is no intrinsically meaningful mapping between the number 1 and the company BMW. I could have assigned BMW to any other number or to no number. So within the family category of numerical data, we can distinguish 3 different subtypes of numerical data: discrete, interval, and ratio. I will begin with discrete data. Discrete data reflect countable things and are represented as integers or whole numbers. So one example is the population of a city. The number of people living in a city is countable, and it's a whole number. For example, there are 422,000 people in the city of Wellington, New Zealand. There are not 422,000.2 people. This means that the precision of the data is limited to whole numbers, and that limitation comes from the data. It does not come from the measurement device. And this brings us to interval data. Interval data are numerical values with meaningful intervals and arbitrary precision. Arbitrary precision means that the precision of the data is limited by the measurement device and not by the data itself. So here's an example. Let's say it's 24 degrees Celsius outside. A more precise thermometer might read 24.43 degrees Celsius, and an even more precise thermometer might read 24.4323492184 degrees centigrade, and so on. So the precision of the data is limited by our measurement device and by the application. For example, we need a higher precision thermometer to monitor a chemical reaction in a lab compared to the average outdoor temperature in a city. On the other hand, 0 degrees centigrade does not mean the absence of temperature. 0 degrees Celsius is a quantifiable amount of temperature, as is minus 24 Celsius. So the interpretation of 0 is important in statistical data types. In fact, the interpretation of 0 is the key feature that distinguishes interval from ratio data. Now, why do we care so much about 0? Well, this has implications for the kind of math that we can apply with interval data. So, 20 degrees Celsius is 10 degrees warmer than 10 degrees Celsius, but it is not twice as warm. You can apply addition and subtraction to interval data, but you cannot apply multiplication or division. To see why, let's consider the physical meaning of 0 degrees Celsius. It is the amount of kinetic energy in atoms such that pure water freezes at mean sea level. It is physically possible for atoms to have twice that amount of energy, but 2 times 0 degrees equals 0 degrees, which makes no physical sense. Here's another example. Twice the atomic energy as at minus 10 degrees obviously does not give 2 times minus 10 equals minus 20 degrees. Okay, so this brings us to ratio data. Ratio data is interval data that also have a meaningful 0, which means that we can use multiplication and division with ratio data. An example is height. A building that is 10 meters tall is literally twice as tall as a building that is 5 meters tall. And 0 meters means the complete absence of height. Now, ratio data usually cannot take on negative values. There's no negative height. Just like a line cannot have negative length, nor can a balloon have negative volume. For convenience, though, negative numbers can be used on a ratio scale to indicate an opposite. For example, negative height can indicate underground constructions, negative money can indicate debt, and so on. Okay, so that's about numerical data. Now I will discuss categorical data. Categorical data are also called labeled data. These data come in categories that may differ on many features. For example, high school versus university are 2 categories of a variable called education level. but the difference between a high school degree and a university degree involves many educational, academic, social, cultural, and economic factors. So now I will discuss the two categories or two subtypes of categorical data. Those are called nominal and ordinal. I will begin with nominal data. Nominal data are discrete and non-sortable, which means that we can assign numbers to the categories, but there is an arbitrary mapping without any relationship between the numbers and the categories or amongst the numbers themselves. So let's imagine we have a survey where people report the genre of movie that they most recently watched. Movie genres include, sci-fi, rom-com, that's short for romantic comedy, documentary, action, drama, and so on. Now, we can assign numbers to these answers, like sci-fi equals 1, and rom-com is assigned the numerical value 2. But that mapping has no relation to the genres themselves. I could have set rom-com equals 1 and sci-fi equals 2. So we also cannot perform mathematical operations on those mapped numbers. For example, 2 sci-fis does not equal a rom-com, nor does a rom-com have twice the genre as sci-fi. It doesn't even make sense. That said, some kinds of categorical data can be sorted, and this brings us to ordinal data. Ordinal data are discrete data that can be sorted by at least one metric. So let's return to the example of education level. Levels of education can take on several values: middle school, high school, bachelor's, master's, PhD. These are discrete categories, but they are sortable. A bachelor's degree is beyond a high school degree, and a master's degree is beyond a bachelor's degree. Now, we could assign numbers to these categories. For example, middle school gets mapped onto the number 1, high school equals 2, and so on. However, the differences between categories and their assigned numbers are not meaningful, nor are they equal. In other words, the difference between a high school and a bachelor's degree is not the same as the difference between a bachelor's degree and a master's degree. And 2 high school degrees do not equal 1 master's degree. Now, it is possible to change the data type by changing the way that the data were collected. Let's go back to the movie genre example. Imagine that you asked people to order the genres according to their preferences. So, for example, someone likes sci-fi the most, and then action, and then documentaries. Now these data are sortable. We can assign numbers to them, and those numbers have meaningful relationships. And so therefore, we have transformed the data from being nominal into ordinal. In the next chapter, you'll learn that interval and ratio data can also be converted into discrete data in order to create histograms. Concerning math with ordinal data. Formally, you cannot apply arithmetic to ordinal data for the reasons that I explained above. However, math with ordinal data is done in many applications. It is awkward to interpret, but it's so commonly done that we just accept it. Let me give you an example. I hope you enjoy listening to this audiobook, and I hope you enjoy reading the book. If you do, I also hope that you give it a rating on whatever website you bought the book from or are listening to this podcast on. You can rate products using 1-star, 2-star, 3-star, 4-star, or 5-star. Now here's a question. Is the difference between 1 star and 2 stars the same as the difference between 4 stars and 5 stars? Is 4 stars exactly twice as good as 2 stars, which itself is exactly twice as good as 1 star? Can you add 2 low ratings to produce a higher rating? Well, the answer to all of these ridiculous questions is no. Ratings are ordinal. They are not numerical. So these ratings should not be summed. They should not be divided to produce an average rating. But, of course, they are. Every website that has ratings displays averages, and consumers use those averages to make purchasing decisions. Now, is this an egregious violation of statistics with terrible consequences? No, it's not. The average rating is certainly insightful, it's helpful, it's useful, and we do not need to be so strict about which analyses can and cannot be done with each data type. Now, this may sound like a trite example, but it is quite profound. Statistics are full of assumptions, requirements, and rules, some of which are important, while others can be bent or broken. There is a gap between pure statistics and applied statistics. The former is necessary for algorithm development and rigorous mathematical proofs, whereas the latter allows us to use statistics here in the real world. The thing is, the real world is messy and it's complicated, and we will never make any progress without bending a few statistical rules. My hope is that by the end of this book, you will understand when and why the rules can be bent and assumptions can be violated. Section 2.7, From Anecdotes to Populations. You know that datum means one data point, while data means more than one data point. But there are finer gradations that have implications for the kinds of statistical analyses and the kinds of conclusions that you can make with data. I will list and briefly define those gradations, and then I'll have a longer discussion about them. But first, let me define the sample size to be the number of observations in a dataset. For example, if you survey 1,000 people about their life happiness and coffee consumption, you have a sample size of 1,000. Do not confuse sample size with the total number of data points. This dataset has 2,000 data points, 1,000 people giving answers about happiness and coffee, which comprises 1,000 samples and 2 features. So sample size is often denoted the capital letter N, sometimes a lowercase n. So in this case, in this example, N equals 1,000, although the number of data points is 2,000. So 1,000 observations, 2 features per observation. Okay, so let me start by defining speculation or theory. Here we have N equals 0. Developing new ideas, hypotheses, and theories can be done without a single datum. Though critical to the development of science, non-empirical studies with N equals 0 are not relevant to statistics books, certainly not this one. Next, we have an anecdote, that is N equals 1. An anecdote is a story of what happened to one person. Next, we have case report, also N equals 1. A case report is basically an anecdote, but in the context of medicine. It is usually a narrative of the diagnosis or treatment of one patient with a rare medical condition. Case reports may have more than one patient, so N greater than 1, but the sample size would still be very small. Next, we have sample. Above, I defined sample size. The sample is the collection of individuals that you measure data from. For example, if you want to know how much meerkats weigh, you cannot measure all meerkats that have ever existed. Instead, you measure a sample of meerkats. Next up is a pilot study, sometimes called small n. No, a pilot study is not a research project about our heroes in the sky who bring us from our cold, wet home to sunny, sandy beaches. Instead, a pilot study, which is also sometimes called an exploratory study or a proof of principle study, is research done using a sample size that is too small for rigorous statistical analysis, but large enough to determine if the equipment and the experimental procedure is suitable. Pilot studies provide an opportunity to change the experiment protocol before collecting the full dataset and demonstrate to a funding agency that the research team is capable of completing a larger research program. Next, we have small-scale versus large-scale studies. These terms are somewhat ambiguous because there is no specific sample size that separates small from large. It depends on a variety of factors, such as the effect sizes, the difficulty of acquiring the data, and common sample sizes within that area of research. A key advantage of large-scale studies is that they have more statistical power to control confounding factors, identify small effect sizes, and generalize to larger populations. Next up is observational study. This is a confusing term. Data are observations, so aren't all studies with data observational studies? The term observational study indicates that the data were collected without any experimental manipulations, that is, without introducing any interventions or controls. An example of an observational study is determining whether men or women are more likely to go to the gym in January versus June. The opposite of an observational study, in which the researchers manipulate certain variables, is called an experimental study. Next up, we have convenience sample. A convenience sample is when researchers expend little effort to acquire the data. An example of a convenience sample is if you only ask your family and friends to participate in your research study. Convenience sampling limits generalizability because the convenient group might be different from the wider population. Convenience sampling should be avoided whenever possible, although it can be acceptable for pilot studies. Finally, we have population. A population is the set of all things that you want to understand. In many cases, the population is impossible to measure. For example, all the stars in the universe. And this is why samples are analyzed instead. Section 2.7.1, Sample versus Population. Although individuals can be interesting, most research has the goal of understanding populations. A widget-producing company, for example, doesn't want to sell widgets to one person. They want to sell widgets to lots of people. Psychologists want to understand how people think, feel, and act, not just one person. Oncologists want to cure all cancers in everyone, not just one cancer in one person. Some populations are small enough to be measured in whole. For example, let's say we are interested in the salaries of all the people who work in one particular department at one particular company. Or maybe we are interested in the ages of all the lions in one particular zoo. Those are our populations, and we can literally measure data from every single member of the population. But many populations cannot be measured in their entirety. Let's say we want to know the average height of Italians. Someone on Wikipedia claims that there are approximately 140 million Italians. It is simply infeasible to locate every Italian and measure their height. So instead, we select a smaller number of Italians, maybe, a few hundred, and we measure their height. That is our sample. The point of sampling is that we want to generalize to the population. Notice the logic here. We want to know the height of all Italians, but we only measure, say, 100 Italians. Now, we don't really care about those specific 100 Italians. We want to make a scientific claim about all Italians based on a sample of Italians. In other words, we want to generalize from a sample to a population. But is our logic solid? Can we really make claims about a population based on a sample? The answer is a conditional yes. Yes, we can generalize, but only if certain conditions are met, namely that the sample is random, representative, and sufficiently large. I will have much more to say about this in Chapter 9, but generalizing from a sample to a population is so important that I want to plant this idea into your thoughts now. It really is the heart of statistics. Section 2.7.2, Big Enough Samples. What sample size is sufficient to allow generalization from a sample to a population? That is an important question, and unfortunately, one that is impossible to answer generally. I wish it were as easy as, for example, quote, n equals 30 is a big enough sample, end quote. The reality is that an appropriate sample size depends on a number of factors, including the effect size, variability in the sample and in the population, how closely the sample characteristics match those of the population, how the samples were collected. There are also practical considerations on sample size. Some groups of medical patients are rare and difficult to access. Some research is expensive and constrained by a limited budget. Some research is time-consuming, but done by a PhD student who is under pressure to complete their dissertation in a timely fashion. You will learn more about estimating appropriate sample sizes in Chapter 17. For now, keep in mind that larger sample sizes are usually better than smaller sample sizes. When I say better, I mean lower risk of statistical flukes and more generalizable to the population from which the sample is drawn. On the other hand, really large samples are not always feasible. Furthermore, bigger sample sizes are not necessarily better. More data is beneficial only up to a point. Section 2.7.3, Problems with n equals 1 studies. Case studies and anecdotes can make great stories, but they must be interpreted with caution, especially if the goal is to understand a population. I do not mean to suggest that n equals 1 reports should not exist. They can be interesting and inspiring. Someone might develop an entire research line just based on an anecdote or a clinical case report. But the real research with rigorous statistical analysis and generalizability happens with larger scale studies. Why are n equals 1 reports difficult to interpret? Well, the main limitation is that the observation is likely to be non-representative. Indeed, the case must be unusual, otherwise it would not be reported. It's the same reason that the news reports big, important things that are unusual. They do not report about some guy who lives somewhere and had a completely normal day, just like millions of other people's day. So this means that statistical inference and population generalization are extremely difficult with an n equals 1 study. On the other hand, having a large sample size does not guarantee perfect statistical inference and generalizability. There can be sampling variability, noise, outliers, problems with the experiment, incorrectly done statistics, and so on. The point here is that case reports and anecdotes cannot be generalized, whereas larger scale studies proffer the possibility of generalization. Section 2.8, Data Management. Data management refers to a system for documenting, storing, and archiving your data. Depending on the nature of the data, proper management might include security restrictions or anonymization. Data management also involves the code that you use to process, visualize, and analyze the data. Data management is important because nicely formatted and organized data are easier to work with and to share. Data management will also help you anticipate problems and share your data. We all have limited time here on our lovely planet Earth, and proper data management gives us more time to spend on enjoyable and insightful analyses and less time struggling with poorly documented and confusingly formatted data. Fortunately, data management is easy, and putting in some effort beforehand will help ensure high-quality data. To manage your data, you need a plan. A data management plan must be custom-tailored to each dataset and experiment protocol, so I cannot give you a generic one-size-fits-all recipe. So, before collecting your data, Craft or adapt a data management plan by thinking about and writing down your protocol for naming, organizing, storing the data and the code files. Also, consider how you will identify and import the data files into your code. Finally, a good data management plan includes data backups. The mechanism of backing up depends on the nature and the size of the data, but the most important thing about backing up data is to keep multiple copies of the data. A good data backup system might include one copy of the data stored on an external hard drive in your office, another copy on your laptop, and maybe a third copy on a cloud storage system. Many research institutions and large companies have in-house data archiving systems. Just be aware of possible restrictions in case of sensitive data. Medical or financial information may be prohibited from storage outside of secured locations. Section 2.9, the ethics of making up data. Well, this sounds straightforward, right? Don't make up data. End of message. Let me add some nuance to that. Making up data isn't problematic on its own. In fact, I created a lot of fake data for this book, and I will encourage you to create a lot of fake data when learning from this book. And I create a lot of fake data in my other books, online courses, and in-person teaching. Other people might use terms like generating data or simulating data, but at the end of the day, it's the same thing as making up fake data. Generating fake data is great. Simulating data is an invaluable way of learning statistics. Creating and working with fake data allows you to develop confidence and intuition about statistical analyses in ways that are not possible when only using real data. I will unpack and justify this claim in Chapter 5, but the conclusion is that the data creation process allows you to control effect sizes, noise characteristics, data distribution shapes, sample sizes, and other factors that are crucial to understand yet impossible to manipulate in real data. Claiming that fake data are real is terrible. Now, this is what most people think about when asked about the ethics of faking data. The problem is not with fake data per se. The problem is presenting fake data as if they were real data. Now, we can differentiate faking from manipulating data as coming up with an entire data set, faking data, versus intentionally changing a real data set in order to obtain a specific outcome. That's manipulating data. But the ethics of both are the same. Don't do it. If you get caught claiming that fake data are real, you might lose your job or your reputation. If you're working with other people, they might lose their jobs or reputations. If the data have real-world implications, for example, safety data in a manufacturing plant, then faking or manipulating data can literally put other people in physical harm. And, even if you don't get caught, you don't want the stress, anxiety, and fear that comes with lying. We live in a complex and uncertain world with many sources of social, economic, health, and climate stressors. Please do not add faking data to the list of things to worry about. Everyone makes mistakes. Mistakes are part of being human. The difference between mistakes and manipulation is that honest mistakes are unintentional, whereas faking or manipulating data is intentional. If you realize that you made a mistake, admit it, apologize, correct it, learn from it, and move on. Conclusion: faking data is an excellent way to develop deep intuition for data visualization, descriptive and inferential statistics, limitations of various analyses, and the impact of data characteristics, including sample size, variance, outliers, and distributions. Faking data is also an excellent way to illustrate hypothetical data patterns to students, colleagues, or customers. The problem comes when presenting fake or manipulated data as if it were real data. The conclusion here is that you must clearly indicate fake data as being fake And maybe you want to use more palatable terms like simulated, generated, hypothetical, or theorized. The point is this: do not allow for any possibility of misinterpretation or ambiguity about the veracity of the data. A more thoughtful and honest discussion. It's very easy to write in a textbook or to say out loud on a podcast, don't do ethically questionable things. But reality is rarely so black and white. There are myriad choices that we make during data acquisition, selection, and cleaning, and when choosing analysis methods and parameters. It may be difficult to know if you are unconsciously introducing subtle biases into the analysis pipeline that make a desired outcome more likely. Now, a purist statistician might disagree with this statement and would counter with the advice that the entire data processing and analysis pipeline should be set in stone before the data are even collected, with no deviations unless an entirely new data set is collected. I certainly sympathize with that sentiment. Using a predefined data pipeline is an ideal that every data scientist should strive towards. But I prefer to live in reality. We humans are developing increasingly sophisticated and amazing ways to measure the biological and physical world. Data sets are getting bigger and more complex. The correct ways to analyze data might not be fully knowable before having the data. And science requires constant improvement and flexibility. The reality is that statistical analyses are done iteratively, each time improving and refining the pipeline. Iterative analysis pipelines can allow for insightful but subtle patterns in the data to be revealed, but run the risk of introducing biases that can affect the results. There are principled ways to increase analysis flexibility while minimizing biases. You'll read more about this in Chapter 18. My goal here is to express my belief that although absolutist data ethics sounds authoritative and is very easy to write down and state, a mature and nuanced discussion of the reality of modern data analysis is more beneficial. End of Chapter 2.